Hello, and welcome to problem number 19, where we're removing the nth node from the end of the list. This is a very exciting and a very fun one because I loved linked lists. Linked lists are so fundamental to learn in C++. Use them all the time. The concepts, everything about it is so trivial and basic, and you need to understand how linked lists work. And this is a great way to learn a beginner versions of linked lists. So here we have a problem where you're given the head of a linked list and you want to remove the nth node from the end of the list and return its head. So this is a little bit more complicated than just removing the nth node. So you're given a list, 1, 2, 3, 4, 5. The values really don't matter, they're just here for representation, at least for our logic purposes. So we want to remove the nth node, and it is from the end, and we see that n equals 2 over here. As we can see at the top, we start here, this is the first from the end, and then the fourth was the second, and you see how it's not there anymore, it was removed. How do we do this? Well, let's first talk about what is a list node. A list node is a class or an object where it holds a value, and it holds the next list node pointer. So what this means, we don't really care about the value right now. The value just holds the number, so let's say it's a 3. The next holds a pointer address to a memory to another list node. And this list node has everything that the previous list node has. It has a value and it has a next. So this can either connect to another list node or it can connect to a null pointer, which is just nothing. There's no memory address it's connected to. So what can we do with this information? Well, now that we know that each of these is a list node, it's not a list, it's a list node, and they're all connected to each other, how do we get rid of the nth node? Well, there's no way to do list node dot count. There's no way we could just get the last node, like with a simple like command or something like that, because they're only pointing one at a time. So we have to iterate through as you can see, we have to iterate one by one. We have to go to the next, and then we have to go to the next, and then we're gonna have to go to another list node, and then to another list node, and we just have to keep continuing on until we reach that null pointer, and that is the end of the list. Okay, so here's a representation of this list right over here. We want to remove the second last of the list, which is, as we can see, the fourth. So we have 1, 2, 3, 4, 5. These are the nth from the end of the list. And we can see that n equals 2 over here, so that's what we want to remove. Okay, so one way we can do this, very simple, very easy, is we iterate through the list one by one, one by one, one by one, one by one, all the way till we reach null. And that's how we know we're at the end of the list. So we'll count back from 5, so it'll be 1, and because n equals 2, 2, we would remove the fourth node. Well, how do we remove a node in the linked list? We just have to erase this pointer that points to the fourth address, to this list node address, and then we redirect it to 5. So now the new list is very simple. It just goes from 1, 2, 3, follow the arrow, 4, and I mean the value still is 5, but it's the fourth node in the list. But here's the problem. You see how the arrow is only pointing one way? We can't just reach to the end, get to null, and then count backwards. Because there is no, as you can see, there is no arrow pointing backwards. We could always make this a doubly linked list and go back and forth, but this isn't the option here. We want to solve it with this problem. So, okay, so what we can do here to solve that is that we have an iterator, and we're going to use green as the iterator for the regular iterator. And then we have an n iterator that is orange. We want to have a count variable, and we will initialize it to 0. This count variable is going to make the n iterator basically lag behind. Every time the iterator increases by 1, we are going to increase the count by 1. And once the count is equal to n, then we start iterating the n iterator. So let's start this iteration process. Go up by 1, and now we increase count by 1. Now we iterate again, and now we increase count to 2. Okay, we see that count is now equal to n. So on the next iteration, we move it up, and now we move up our n iterator. 1. We iterate again. 2. And now we iterate one more time. Boom, we're at the end of the list, so we don't want to iterate anymore. So we landed on 3. So why did we land on 3 instead of landing on 4? Because 4 is what we want to remove, right? Well, as we said before, these arrows are what we are trying to reroute and remove. We don't really care about this because once this is once 3 isn't connected to 4, basically 4 is a lost object in space. So we get rid of this next variable and we reroute it to 5. And now we remove the block and we have our correct output of 1, 2, 3, 5, as we can see here. That is the logic. So how do we code this? Okay, now that we're here on Leetcode, we can see that it gives us the structure of a list node for a singly linked list. So it holds a value and it holds a pointer to the next list node. Using our logic, we had 2 list node pointers. We had a list node iterator, and we set that to head. And then we had a list node end position, and we set that to head as well. So, but here we'll set it to null pointer for the logic purposes. And also we had another variable called count, and we set that to 0. So in our logical representation, we had a while loop, and the iterator keeps continuing until it reaches null pointer, like we said earlier. And we just set the iterator to equal to iterator next. Now let's get to the logic. So, like we said before, we had a simple if statement. If count equals n, we want to initialize the end position to equal to head. Once we do it this way, because then now we can make a simple if statement where end position, if it doesn't equal null pointer, so if we initialize it to the head, we iterate it. This is just a simple and easy way of doing it. There's probably millions of other ways. All it does is if count equals n, so once count increases, we have to add that here as well. So let's add that real quick. Once count increases to whatever n is passed to, let's say for the example it was 2, it will lag behind 2 positions. The reason that we have this if statement before this one is because if we put it over here, then it will initialize the head and it will iterate right away. So instead of it being initialized at the head, it's going to be initialized at the second position and it's just going to throw all the logic off. So we keep it behind, and pretty much when this is initialized, this won't even matter anymore because count is going to keep iterating. And so we probably lose some performance here, and there's a better way of doing this, but it's just a simple explanation on representing our logic that we decided for the algorithm. So now we have to implement the part where we're removing the node. We have the position of the node that is connected to the node we are removing. So call that end position, and if it's not null pointer, then we want to check if end position next is not null pointer, because we are setting end position next to its next position. So here, let's have a simple explanation of what this means. So let's say the 3 is connected to the 4, and the 4 is connected to the 5. We are basically saying that the next position, so end position 3, the next, this pointer, is equal to this pointer over here. And all this does is basically just remove the connection like this and sets the next to 5. But if next is a null pointer, then we're going to get a null exception error if we try to do this, because null pointer doesn't have a next. So we're just going to set end position to null pointer, or end position next equal to null pointer. That's usually if we're removing like the last variable on the list. If this all works out, we want to return head. But we have a dilemma, because if we want to remove the first part of the list, we will never get an end position, because n will be too high and count will never reach n. So
end position will never be initialized. And if we have that problem, we know we just have to remove the first list node in the list, and there's a simple solution to that.
That if end position is never initialized, we just have to remove the first part of the list. So the way we do that is just we return head next, and it removes the head. So here we are looking at the code at its fullest extent, and let's submit it and see what happens. As we can see here, applause! 100% it beats in runtime, which is probably incorrect, and beats 91% in memory. That's actually, and that one might be correct. I don't understand Leetcode ever. It never makes any sense. Maybe we can analyze the complexity. Here we see that the complexity is O of n, just like we said earlier, because we are only iterating through the list one time. And that is what our goal. We didn't want to add any more, like, going back and forth. If you like this tutorial, please like and comment. And if you have any questions, please comment below. I will respond instantly. I'm on the search for learning, and I'm ready to learn with you guys. So, without further ado, I'll see you in the next video.